This is an introduction to energy. So you probably have known some words about energy that you've used in other science classes, such as potential and kinetic energy. If you remember the classic example of a car on top of a hill, the car on top of the hill has a lot of potential energy. Potential energy is energy that has potential, meaning it's stored. While the car's not doing anything right now, it has the ability to do something. In energy, in this energy unit, energy gets transferred rather than just created or destroyed. We have a lot of transfer of energy. So that energy up on the top of the hill can be converted or transferred into what's called kinetic energy. And that's when the car starts moving down the hill. So kinetic energy is energy in motion. So now we have kinetic energy. Another type of energy that we're going to be talking about involves chemical energy. So for example, a tank full of gasoline has a lot of chemical energy. Chemical energy is stored in the bonds of the chemical that makes up what we're talking about. And this energy right here that this gasoline has, if actually maybe lit on fire, the gasoline has a lot of energy that can then go out to be thermal energy. So all of that stored chemical energy has the potential to actually turn into chemical energy and release that energy from its bonds. So it's another type of energy. In general, energy flows in a certain direction. And so in order to talk about how energy flows, let's take a look at this hot cup of hot chocolate. So our hot chocolate is really hot. And let's say you have really cold hands, right? And you've probably done this on a really cold day. You take your hands and you put them around your hot chocolate, right? Because you want to warm up your own hands. So here's your cold hand surrounding your hot cup of chocolate. Well, what happens? Well, what actually happens is, if we take our cold hand, is that the heat flows from our hot object into our cold hand. So heat always goes from temperatures that are hot to temperatures that are cold. So from hot to cold. So in a sense, you're stealing the heat from the hot chocolate. This transfer will stop when the two have kind of reached a similar temperature. So what's actually happening is your hot chocolate is no longer going to be as hot because that energy is being transferred into your cold hands. And your cold hands are now going to feel warmer. This heat transfer is known as thermal energy. Thermal means heat. So we are transferring our heat from hot to cold. Some other terms that are important to know for this chapter involve a system and our surroundings. So a system is basically anything that we're taking a look at where kind of the reaction is occurring. Our surroundings are everything around it. So for example, if we're doing a reaction inside of a beaker, as seen in this picture, what's happening in the beaker, the reaction, is considered the system. Therefore, anything else around it, like our atmosphere or our classroom, is considered the surroundings. The surroundings. Okay? So if we take a look at two other important words, let's first start with the word exothermic. Exo sounds like the word exit. Thermic means heat. So in an exothermic reaction, heat exits from a system into the surroundings. So if we were to take our previous picture and show that, here's our system. Whenever the reaction occurs in an exothermic, the heat leaves the system and goes into the surroundings, right? So here's my heat leaving the system into my surroundings. If this occurs, that is called an exothermic reaction. Heat is exiting. On the flip side, we have something called an endothermic reaction. And as you can guess, it's opposite of exothermic. Endo sounds like the word enter, endo, enter. And so in this type of reaction, heat is entering into the system from where? The surroundings. So let's draw a picture that represents that. As we know, our surroundings has a lot of heat in it. Any of that heat can be used and transferred into a system to warm it up. So heat is entering into the system from the surroundings is an endothermic reaction. Okay? So, for example, if I have an ice pack, that ice pack starts off really cold, and eventually what happens is heat from the surroundings, heat from anywhere around it, can actually enter into that ice pack, and over time turn that ice pack to now maybe more room temperature, so it's not as cold. So heat entered into the ice pack from the surroundings, and the ice pack is the system. Therefore, that example, an ice pack then becoming more like room temperature, is an endothermic reaction. Going back to an exothermic reaction can be any type of reaction that releases heat. You can have an explosion. You can have something as simple that we've seen already in lab when hydrochloric acid and a metal come into contact, tons of gas forms and your bottom of your test tube is hot. Heat is leaving that reaction. Okay? All right, so we're going to actually look at how you can display exo and endothermic reactions on a graph. But before we do that, I have to introduce this word, which is enthalpy. Enthalpy a lot of times is represented by the letter H in chemistry. So what enthalpy is, it's more of it's the amount of heat, it's the heat content of a system. Or it's actually a better way to say it, it's the potential to create heat. So using an example can really help you understand enthalpy, okay? So for example, if I look at this picture here, I've got just a log and ashes. The log has more enthalpy than ashes do. Why? Well, let's bring back our definition. A log has the potential to create heat, meaning it has more ability to create heat. Why do the ashes? Well, the ashes have already been through a reaction, and there is not much substance there that can catch on fire to create heat. It looks like they've already gone through the process. Therefore, just your ashes sitting down, on the floor don't have as much potential, so they don't have as much enthalpy. Whereas this log, if I were to light it on fire, definitely has the potential to create a lot of heat. Okay. Now, taking that into consideration, how could we then display that on a graph? So if you look here, I've got my x and my y axes. And on my x-axis, I've got an exothermic reaction. On my y-axis, I've got H, which if you remember, H means enthalpy. You might want to put that in if you want to remind yourself, enthalpy. So if you notice, my enthalpy is increasing on my y-axis here. So for an exothermic reaction, let's think about that log example that I just talked about, right? The log. The log has a lot of potential, right, to create heat. Therefore, it has high enthalpy. So where would high enthalpy be? Well, this is an increase in enthalpy, so we'll put it up here, right? And we'll label this as my log. This little bar right there will represent my log. And now, bringing back that same example, right, the ashes, right? My ashes have low enthalpy. So again, enthalpy down here would be low enthalpy. So this is like my ashes. Now the reason why again my ashes have low enthalpy is because if we were to take something like the log and light it on fire and all is said and done, when the reaction is over, all I have left are ashes, maybe a little bit of carbon dioxide, right, some gas, some water vapor. Those things don't really have the ability or don't have as much potential to create heat anymore. They're done with. So because they don't have as much potential, maybe they have a little potential, but they don't have as much, they're lower down, they have less enthalpy. That is exactly what enthalpy is. Okay? So on the graph then, if you notice, I can kind of make a relationship between these two, right? Because that's really what's important for us, is being concerned about the change that occurs, right? In science, we're more interested about the change in the process when we talk about energy. So what is the difference, in other words, from beginning to end? If we're going to light that log on fire and turn it into ashes, what is the change that occurs? That's more important to look at. So let's write some of those things down. Okay, we're concerned about the change in this process, which is the difference from the beginning to the end of the reaction. We use a triangle, which is known as delta, Greek symbol delta, to represent change. So if you notice, my H, which represents enthalpy, has a triangle in front of it. It means there's the change in enthalpy. In other words, it's showing what's happening from beginning to end of this reaction. And my change in enthalpy in this reaction has decreased, right? The log, when it turns into ashes, has less enthalpy. It has less potential. Okay, so enthalpy in this instance goes down because heat is given off. Right? That log releases a lot of the heat, and there's less heat available when it turns into the ashes. So enthalpy goes down. Therefore, the way we represent that in our change of H is we say we have a negative change in H. Negative, as in I've lost that heat. Negative represents a loss of heat. Again, to turn from a log to ashes, you've got to lose that heat. All right. Now let's look at an endothermic reaction. Hopefully you realize that this is going to be, again, an opposite process. So let's bring back that cold ice pack that you have. That cold ice pack, it doesn't have, sitting there cold, it doesn't have that much enthalpy. It doesn't have that much potential to create heat. It's very cold. So we're going to put it down here as a cold ice pack. Now, when I use the ice pack, right, if I use the ice pack, it then draws in the energy from the surroundings, right? If I leave that really cold ice pack out, all the surrounding heat can get to that ice pack, right? So now, in a sense, the ice pack has absorbed the heat from the surroundings. So it has more heat in the end. We'll call this the used ice pack. And it's no longer as cold because it has absorbed that heat. Therefore, I have a lot more enthalpy. My enthalpy goes up. This used ice pack has a lot more potential to create heat because it has heat now in it. So my enthalpy goes up. So therefore my change of H is a positive change in H, meaning heat was absorbed. So these are our two graphs, if you can kind of tell the difference between them, an endothermic versus an exothermic. That's the end of energy.